Maybe. No, you know what? The sound didn't work first period, so I don't know what's going on with this thing. Bumming me out, man. Like, wasn't even like bad sound, like there's no sound. Trying to turn up the volume a little bit. Well, usually I do. Yes, Payson. Yes, Payson. Okay. Did you say it's hot in here? 2x plus 2. That's when you add the bases together. That's not quite right. Not quite. I'll show you. All right, so let's do this first one. Let's figure out the area or the integral from 0 to 2 of f of t. Okay, so we're going to go 1/2. What is b1? 2. What is b2? What's this height right here? If this is 2, 6, because I take that and plug it into here. Okay, so it'd be 2 plus 6, and then the height is 2, so that works out to be 8. Okay? It's just a variable. What did I... Nothing. Kind of, yeah. Right, yeah, right here. No, I use 2 for the x right here. Right. Yeah, they're pretty much the same. Yeah. Okay. All right, now the next one says let's do the same thing from 0 to 4. So I'm going to change this to 4. So for part B, if I want to do the integral from 0 to 4 of f of t, oops, I forgot the dt there. I'm going to go 1/2. What is base 1? No, 2. Always 2. Okay. This one right here will never change because the y-intercept is always 2. Okay. Plus 10, because if I take and plug 4 into here, I get 10, okay, times the height, which is 4. So that gives me a final answer of 24. Okay? Okay? All right, now here's the fun part. Now we're going to do it from 0 to x. So we got to figure out with a variable. Okay, so I'm still going to go 1/2. What's the height of base 1? 2, because that's the y-intercept of the graph. It's not changing. Plus 2x plus 2, because we always got the other height by plugging in whatever that number is into the equation for the line. Yes. If you would like, yes. And then what is the base going to be? Good, x. Okay, so if I simplify this a little bit, that's 2x plus 4 times x, which is x plus 2 times x, which is x squared plus 2x. Okay? All right. Is there another one? Oh, okay. So now we can take that and plug in 2 and 4 and 0. We already have the general formula, so nobody cares about that. All right, now let's play again. This time we're going to go into the negatives. Okay? All right, so first of all, what is c of 2? In other words, what is the integral from -1 to 2 of f of t dt? So I'm going to make this a 2. What's the base? 3. I guess it's a triangle, so I have to go 1/2. Base, you guys just said, was 3. What's the height? This is the same line as we had before. This is still 2t plus 2. 6. Because if I plug 2 into there, then I get 6 as an answer. So half of 3 times 6 is 9. What is the integral from -1 from the previous graph? But it's the same. Right, it's a triangle because they're going all the way down to -1. The other one stopped at 0. But it's the same line that's defining the triangle as the line that defined the trapezoid. You're right, that's not entirely clear. Okay, so now we're going to go from -1 to 4. So the base is 5, yep. And the height is 12. No, you're right, 10. You plugged in 5. I plugged in 5 also. But x is 4, so we're plugging 4 into there. Sorry, so the height is 10. So that means the area, or the integral, is 25, okay? How about from -1 to -1? Don't even... the negative part is only if it's underneath the x-axis. No, I did the whole triangle, 1/2 base times height. I used the same equation for this line, but since it's going all the way down to the x-axis, now the shape is a triangle, not a trapezoid. So I have to use a different area formula. All right, here's the kicker. -1 to x. Because remember what we're trying to do is we're trying to come up with a general formula that we can use for these, for x instead of... So it's going to be 1/2 times the base. What would be the base if this is just x now? X plus 1. Right? Because whatever this was when this was 4, I actually added 1 onto that. It's x minus -1, so it's x plus 1. What's the height? Good. Times the height, which is 2x plus 2. Okay? I'm going to take half of that just to make my math a little bit easier and call this x plus 1 times x plus 1, which I know is x squared plus 2x plus 1. Okay? You ready? Huh?
I don't see any pattern.
That's the final answer. No, you don't see any pattern. It's true. We still don't know the answer to life, the universe, and everything. All right, here's the punchline, number 3. First of all, we have 3 different area functions, fill in the blanks. So for the first one, when it was just a rectangle, what was the area function that we came up with? 4x minus 4. What was the area function we came up with for the second one? X squared plus 2x. What was the formula that we came up with for the third one? Because it is a race. It is a competition. Everything in life is. Okay. I don't know if this is going to make you feel good or bad about life. But you will see once again in the third column that derivatives have re-entered our lives. What is the derivative of the first area formula? Wrong. What is the derivative? 4. The derivative of 4x minus 4 is 4. What is the derivative of the second one? 2x plus 2. And the derivative of the other one is 2x plus 2. Okay? You should notice a very interesting fact about the derivatives of the area functions. A fundamentally beautiful property. What did you just say? Right. If you take the antiderivative of these, then you get these. In other words, the derivative of this is this. These two things are the same.
So you just plug in the numbers
You guys get it?
Yeah, I guess.
So the integral of the function gives you the antiderivative of the original function. So if you take the derivative of the integral, you'll get back to the original function that you started with. Let me say that again. If you take the derivative, so this table right here were the formulas for the integrals we did, right? And then this column right here is the derivative of those integrals, and it worked out to be the original function that we started with. So if you take the derivative of the integral, those two things cancel each other out, and you're left with the original function, meaning derivatives and integrals are inverse functions of each other. You take the derivative of the function, you just get the derivative of the function. But if you take the derivative of the integral, those two things cancel each other out, and you just are left with the original function. If you're being asked to take the derivative of the integral. Okay? Yes. So that's why these things are in here, that you'll notice that these two things were the same function, but it just had a different starting point. This one started at 0, this one started at -1. And so all that did was change essentially what the plus c was, and then when we took the derivative of that, it just went away.
How do we write that in the equation?
Yes.
How do we know if it's not?
We'll talk about that. Yeah. Okay? We'll talk about that. Okay, so let's pretend we have this function right here. We're going to define one final function, d of x from 0 to x of 0.2 t sine of the cosine of the sine of t. Don't worry about trying to find a simple formula for this right here. The question is, if I take the derivative of this, what do I get? If I take the derivative of this, if I take the derivative of d of x, what do I get? 0.2t sine of the cosine of the sine of t, because derivatives and integrals are inverses of each other, just like addition and subtraction, just like multiplication and derivative or division. Okay? What changed is this symbol and that symbol are now gone, because we took the derivative of the integral, and so those things canceled each other out. Not, it is what you thought it was. Yeah, no, you're going to be fine. You're on the right track, okay? Kind of. I mean, really the dt is the width of those rectangles, okay? All right, so I'm going to just read you this paragraph because it's such an exciting part of calculus, the fundamental theorem of calculus. It's appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. Differential calculus came from finding tangents. Integral calculus arose from a seemingly unrelated problem, finding areas. Newton's mentor at Cambridge, Isaac Barrow, discovered that those two things are closely related. In fact, he realized that differentiation and integration are inverses of each other. Okay? The fundamental theorem of calculus gives the precise inverse relationship between the derivative and the integral. It was Newton and Leibniz who exploited this relationship and used it to develop calculus into a systematic mathematical method. So now we can do integrals very easily without having to compute them as limits of sums like we did in the last two sections. Okay? So here is the fundamental theorem of calculus, part 1. And this is why you're a little bit confused, because there's two ways to think about it. One just involves integrals and derivatives. The other involves antiderivatives, which we're going to get to next, okay? But the fundamental theorem of calculus part 1 just says that if you take the derivative of this integral, you get the function back again. Okay? The derivative and the integral cancel each other out. That's it. Well, kind of. I mean, now, but yeah. Right.
Okay, so what should I put like that? Okay, so
So you should put down derivatives and integrals are inverses. The derivative of the integral equals the function. F of t, yep. Okay, now Maggie's a little bit disappointed by the whole x and t situation, but it is a little bit important, okay? Whatever this variable is, that's what goes into the function, okay? Because the function is just the line. Yeah, the function is just the graph. Yep, exactly. Just defines the graph, okay? Because. Okay, all right. Okay, we're going to get to that. We're going to get to that. Okay, that's the fundamental theorem of calculus part 2. Today we're just chatting about this startling relationship that we just found. All right, so find the derivative of the function g of x equals the integral from 0 to x of the square root of 1 plus t squared dt. Wrong. Payson? Right, plug in the x for the t, so it's the square root of 1 plus x squared. I did, Maggie and I, oh, okay. Maggie and I were chatting about it. Whatever this guy is right here, that's what goes in for the variable. Right. But you could switch it around. You could make these, and that's why, I mean, Maggie's asking, like, why is it t and it's x, and I'm sort of hedging on an answer there because you could change both of those to x's and make this a t, and then it'd just be the other way around. It doesn't matter. I don't think they could both be x's, no. Yeah, right, yeah. I just found out yesterday that you and Emma Jensen are dating. That's what she said, yeah. Shane?
So if the s had
Uh-huh.
plug into the
No. We'll talk about that tomorrow. I don't want to get too ahead of yourself. That's the answer.
I understand that's the function, but if you were to solve that function, or they wouldn't put a number there. What's happening, that's final function.
No, they're going to put numbers there. Yeah, we're going to get in. It's going to relate to antiderivatives, okay? Okay, one tiny thing that you guys need to be careful with. If the thing on top is not just a plain old variable, so in this case it is a x to the 4th, you take, and again we're taking the derivative of the integral, that's the only reason why this works. So these two things cancel each other out, and the answer is secant of this thing x to the 4th, but we're taking a derivative, right? So we got to chain rule that bad boy.
No.
Yes, yes. It says right there we got to chain rule it, so I have to multiply it by the derivative of the thing on top. We're really doing that all the time, even when it's just an x, but the derivative of x is just 1, so it doesn't change it. Okay? What's that? From 1 to x to the 4th. Okay? And Maggie asks a really good question also, or I mean, you're saying is that a 1 or a 2? That doesn't matter. Okay? Because remember when we were back here, that's why they changed this up, to show that in this case right here, we went from -1 to this line. In this one right here, we went from 0 to that line. And remember that the derivative came out to be the same either way. Okay? So whether you go from 0 to the variable or -1 to the variable, it doesn't matter. Those are still going to be canceled out in the end. Okay, and so this is them showing you why that all works, but you guys probably don't care about that. Okay. Okay, in section 5.2 we computed integrals for the definition of as a limit of Riemann sums, and we saw this procedure is sometimes long and difficult. The second part of the fundamental theorem of calculus, which we will get to tomorrow, which follows easily from the first part. Mason is already on top of it. We just have to kind of sort that out in your brain a little bit. It provides us with a much simpler method for the valuation of integrals. But we will talk about that tomorrow. So I'm going to give you guys just a few problems to work on. Yeah. Uh-huh. Is the y on the bottom? Then you just put in a y. Whatever. Then you just put in an x. So Maggie and I were just